All right, so today we are actually going to get into what the title describes. We're going to get into exponential and maybe even talk about the basic idea behind logarithms. Logarithmic. So let me give you this next packet. I love that I turned my camera on just in time to film nothing. It's awesome.
My screen, it's a genius.
You got one? I'll give you one. Everybody got one of those? Here. Oh, all right. So I want to overlap a little bit with the notes with what we talked about already. Guys, we already talked about how to find the inverse of a function, but I wanted to give you officially the little steps here, right? Replace fx with y, because that's what it was. Switch the x and y, solve for y. And we already talked a little bit about why that makes sense. What does the inverse function do compared to the original function? What does f inverse do compared to f? So if f of 2 is 7, what's f inverse of 7? 2. Whatever f does, f inverse undoes it. Is that cool? All right. I like it. You guys are like, sure? Sounds good. Okay. So this idea of switching the x and y and solving for y is exactly capturing that idea. One guy's input is the other guy's output. So switching those is exactly that idea. All right, let me switch the input and output. Switch x and y. And thankfully, that's also what we do visually. That's what we do graphically. It's insane. So here, I'll do this one with you guys, just to remind you guys. So first step, replace f of x with y, because that's what it was to begin with. And then I switch the x and y. And then I solve for y. So you add 4. Who knows how to do that last step real quick? When I have a 2/3 in front of my variable, how do I solve for that variable? Multiply by the? Yeah, reciprocal. I like it. 3 over 2. You can see why it cancels that out. So I get y equals 3 over 2 times x plus 4. And if you want to, you can distribute that. I don't care. That is now f inverse. So the original function subtracted 4, the inverse function adds 4. The original function multiplied by 2 over 3, right? Multiply by 2 divided by 3. This one multiplies by 3 divides by 2. They are opposite functions. It's too nice to believe. So just to really make you guys see what's happening. Take a minute, wherever you want to here, figure out what f of 6 is. Figure out what f of 6 is. What is f of 6? Take a minute and figure out what that is.
Gotta use the whole room. I brought myself this much liquid to get me through today. What kind of liquid is it? Let's see.
Alright, what do you guys get for f of 6? Yeah, 3 goes into 6 twice, times 2 is 4, minus 4 is 0. So then, therefore, what must f inverse of 0 be? If f of 6 is 0, f inverse of 0 must be 6. Because what did f do to 6? It made it become 0. So what's f inverse going to do to 0? Take it back to 6. That's the whole idea of 1 to 1. 6 goes to 0, so therefore 0 goes back to 6. It's 1 to 1. It's a beautiful name. Oh. So let's see, real quick. What's f? If I do f inverse of 0, I get 3 halves times 0 plus 4. Whoa, let me bring it over there. Right? F inverse of 0. I'm going to take 0, the output, and put it as the input. And what happens here? 3 halves times 4 is?
12 over 2.
Yeah, sure, 12 over 2, which is? 6. Hey, holy shit. Well, of course, of course, it's no surprise. That is the inverse function. It should do exactly that. Okay. Yes, ma'am.
So that -1 next to
Good.
F
Yes.
just means it's inverse?
Good. I love it. It's a horrible choice of symbol. It really is. This is so stupid because we're used to -1 power meaning flip. But this is a -1 on a function. It's a different idea. It means the opposite of that function. I like it. So please don't just flip it. That's not the inverse. The opposite of x plus 5 is not 1 over x plus 5. It doesn't make any sense. The opposite of x plus 5 should be x minus 5. I should subtract 5 to undo adding 5. Right? All right, you guys do number 2. Just find the inverse for number 2. Find the inverse. You got all the steps you need right up here, and an example we just did right over there. Just in case somebody's realizing this, we're always talking about real numbers when we're doing inverse function. We're just talking about real numbers. That is why the cube has an inverse. Let me catch up to you guys. I'm going to put it up here. So switch x and y, and then how do I start to solve this thing for x? I mean, for y. Cube root both sides. I love it. First thing I got to do is get rid of that cube. Everything's stuck inside of it. So if I cube root both sides, what happens on this side? These cancel. So you get y plus 4 equals cube root of x. And what's the last step? Subtract the 4. So this, just to write it more officially, is f inverse. That is the inverse function. Cube root first and subtract last. What did this one do? It added 4 first and then cubed last. This one cube roots first and subtracts 4. It does all the opposite stuff in the opposite order, so it is the opposite function. It's the inverse function. Okay. So, I mean, to find the inverse function, if it exists, if there is an inverse function, this is how you do it. Always. So, now, we did an example up here. If I plug the result of something back into the other guy, don't I get back to where I started? This one, I plugged a 6 into F. I took the output, plugged it in an inverse, and I got back to 6. So what would this do? Who remembers this notation? What does that notation mean? What's a better way to write this? So F inverse is going to do something to X, right? We don't even know what F inverse is. It's going to do something. But then what's F going to do to that? What's F going to do? So F inverse could take X and make it become B. And then what's F going to do to that? It's going to do the opposite. It's going to take it back to where it was. So what's it going to do? This is almost too nice to believe also. So watch. We just did this a second ago. We just did it right up here. We did something. If I have X cubed and I take the cube root of it, the cube root and the cube are inverse functions, right? They're the most basic example of an inverse function. I cube 2, I get 8. I cube root 8, I get 2. I went back to where I was. One makes 3 more of them, the other one cuts it in thirds. So of course it's going to undo. Now watch. When I have inverse functions acting on each other, I can just cross through them. They kill. So what's left? X. So look. Let me cross through. This one kills this one. Dead. What's left? X, of course. Because whatever this does to X, F is going to undo it. And it doesn't matter what order I do this in. Whatever F does to X, F inverse is going to undo it. So I get back to where I started. Inverse functions will kill each other. So whatever's on the inside to begin with comes back at the end. It's like nothing happened to them. I'm being cube rooted. Cube will save you, and then X is out. Right? Just to be really wait for a minute. Okay. Blah, blah, blah. So this just captures that idea. The two inverses should kill each other. Bam. So let me ask you this. So here we go. What I want you to do here is what is F of F inverse actually calculated. That's all I'm going to say. Screw it. You guys should know how to do this. Do it. You're like, what do you mean? Well, this is a function, right? Where is it? There. What's this asking me to do? Take that function and put it in. That's the composition stuff, right? Same stuff. Same stuff. Do it.
So they're going to cancel?
Well, you're gonna show me if they cancel.
Hold on, Mike. One other thing for you somewhere. There. Oh, you need this here? Sure. Oh, okay.
In case you're having some trouble, F inverse is this. So I'm going to take this whole thing and put it in there. So this is equal to 4 over. Exactly. So that's just X right there. Plus 2. Ooh, this one looks yummy. What's the easy thing that happens on the bottom? So you get 4 divided by 4 over X. How do I divide fractions? This is 4 divided by 4 over X, right? Just rewriting it. So this becomes 4 times
X over 4.
And what happens there?
X.
There. That is proof that those two functions are inverses, because whatever x is, they kill each other. It comes back to x. Whatever one does to it, the other one undoes it. It comes back to x. That proves that they're inverses of each other. The ideas here are so nice, and then the actual work you have to do is not that horrible if you just do it step by step. This looks heinous as hell, but then those go away. And then that's just dividing fractions, which you have got to get over. Dividing fractions just multiply by the reciprocal, not a big deal. A lot of guys will write this and give up and go, well, that's got too many fractions, that's over my quota. Just do it, just try. I don't know what the heck's I'm going for. Okay. Now, so the first page was more algebraic inverse ideas. This up here is the graphical interpretation. So let me do this one with you. Can you make an XY table for this function as it is? Why is this a function, by the way? Why is this a function? Passes the vertical line test, and why does it have an inverse? It passes the volt, so it's a function. Check. Why does it have an inverse? Because it passes the volt. If inverse exists, check. So to be a function, you have to pass the vertical line test, which is just the visualization of the definition of a function. Oh shit. For every x, there could be only one y. It can't go through more than once. And then instead of twisting the function, I twist the test. The horizontal line test tells me, will there be an inverse function? Oh. Okay. So let me see. Can somebody pick off some points? Can you see any points this thing goes through for sure? I see a couple. 0. -2. What else does it go through?
1.
Looks like 1, 1. Anything else?
4, 2.
Yeah, 2, 4. All right, that's enough. So what would that's for F. What would the inverse table look like? Let me see. Let me put this somewhere better.
0.
Yeah, what would it look like? -2, 0. Because how do you find the inverse? Always. Switch x and y. That's almost too nice to believe. Why is it such a basic idea? Because inverse functions are actually pretty basic ideas. So, -2, 0. 1, 1. That's a boring one. 4, 2. I love it. Switch, switch, switch. And then graph it. Wow. -2, 0. Bam. 1, 1. There, formula, right? 4, 2. Bam. Where does it look like there's a mirror? Right down the center. It looks like there's a mirror. Always. The y equals x line, because since I switch x and y, it's going to flip over the y equals x line. So you guys, believe it or not, this one's actually easier in a way. Do this one. Why does this have an inverse? Passes the horizontal line test. I love it. It's definitely a function. It has an inverse because it passes the horizontal line test. So graph the inverse on top of it. Bless you. Bless you. I like these pictures. They're kind of nifty. Sort of look like crop circles or something. So watch this. I don't have to make two tables. I shouldn't have to. The original function goes through -5, -4, right? So then the inverse is going to go through -4, -5. The original function goes through looks like it wants to be 0, -3, or -3, 0. So this is going to go to 0, -3. You guys following what I'm doing? What's the original go through? It also goes through 2, 1. So what's the inverse going to go through? 1, 2. And then the original goes through 3, 5. So this is going to go through 5, 3. Just switch the x and y every single time. So let's plot these points. -4, -5. 0, -3. 1, 2. 5, 3. It's nice straight lines. You get a little bug or something. I like it. So there's that mirror right here. Good job. Woo! There's that mirror going right down the middle at a diagonal. That's nice, right? That's kind of nice. Okay, how you guys feel about that so far? So finding inverses, what's almost the only thing you have to know to find the inverse in any situation. You just switch x and y. What about this graph? Switch x and y. What if this is a function? Switch x and y. It's awesome. All right, so here are exponential functions. So exponential functions are used to talk about population growth. They're used to talk about exponential decay, right? Do you remember Chernobyl? It's an actual event, not just a horror movie, but Chernobyl, they had that big explosion. There was a lot of radioactivity. They can talk about the half-life of the radioactivity and how long it's going to take before somebody can live there again and not become some kind of a horror movie material, right? So that's, I keep doing this. So from your perspective, it has some radioactivity here, and it's going to decrease over time. It's going to have that shape to it. Now, what if I put a couple rabbits in a room with some food, give them some time, what's going to happen? Well, the population is going to increase in that room, right? Probably want to throw some more food in there every now and again, or else I got a real rabbit horror movie, right? Whoa! Okay. All right. So this shape, this exponential shape, is used not just because we went, well, that looks good, but there's actually proof of it in higher level maths as to why that function is the best to use. But it does end up looking like what I would expect population growth to do. Once there's more people to make more people, and then there's more people to make more people. It should freaking go, wow! So let's try to see what this thing looks like. You guys, here's the function. You guys make, is that me? Oh, you guys make an XY table. Don't forget to put it in airplane mode. Try to graph this thing. Don't say to me, well, we just started studying. I don't give a shit. You know how to make an XY table. You see, where's the X? Where is it? In the exponent. That's the new thing about this. We haven't dealt with functions where the power is the unknown thing. X squared grows pretty quickly. 2 to the x beats that the shit out. It just grows like insane. So if you ever, now obviously I watch a lot of horror movies. I keep referencing horror movies, but you know, like they're the virus movies where they're like it's here and then tomorrow it's going to be here and then the next day it's the whole world. And it's growing exponentially. Or the blob, little blob, and it eats people. It's growing exponentially, right? I don't know if you've ever heard that phrase in a horror movie, especially if you watch the old 50s B horror movies. It's growing exponentially. Oh, it's going to kill us all. Anyway, this is what they meant by exponential growth. It's growing very, very quickly.
You mean what, Joker?
You mean the goblins? Is that similar to that movie? It doesn't really happen, but...
No.
Yeah, unfortunately the virus part could happen. But normally the blobs that eat us don't happen. Or that hasn't happened yet. You never know.
If it does happen, I'm going to the desert. Because it can die easier in the desert.
Okay, hopefully. If that's true, I'll be there with you. All right, you guys go ahead, make an XY table. Here, let me help out a little bit. You've already started, then just incorporate these in there. Do -2, -1, 0, 1, 2, for sure. Those are the 5 biggies. For most functions, you want to at least do those.
Plug it in, calculate it, make a point. Go to the next one. It's the same way we do every XY table ever.
Yeah, what's a negative power mean? Sure, fraction or flip. That's all negative power means is flip. So 2 to the negative 2 would be 1 over 2 squared, which is 1/4. So I got the point, negative 2, 1/4. What about negative 1? 2 to the negative 1 is 1 over 2. So I got the point, negative 1, 1/2. 2 to the 0 is 1. So we got 0, 1. 2 to the first is 2. We got 1, 2. 2 squared is 4. So we got 2, 4. So just got to plot those and connect them. I kind of gave away the shape of this thing a minute ago. Negative 2, 1/4. Negative 1, 1/2. That's a little bit easier. Plot. 0, 1, 1, 2, 2, 4. What would 3 go to? Yeah, 3, 8. Might as well put 3, 8, just so we can see how quickly this thing grows. 4 would go to 16. See, this thing grows really fast. Now, what's happening back here? Here, this is obvious. It's just going up forever. Just growing quickly up forever. You ever heard that stupid little thing about, would you rather me give you $1 million today or give you for the next 30 days a cent and then double that and then double it every day? You would rather do the double every day because that's related to this. It grows so fast we can't even contemplate that by the 30th day it's going to be so many millions. I can't remember. Right? So it's sort of a stupid trick question, and people, I hate those kind of things. That's all math does, is make stupid little trick questions. That's bullshit. But it is kind of nice to show that this thing grows a lot faster than you think. But what's happening back here? Help me out. What would, let me extend our XY table. What about negative 10? What's 2 to the negative 10? That would be 1 over 2 to the 10th. Which is 1 over a lot. I don't know, what would that be, Jeff? You can do it. Can you do it? No, I'm too tired. 1,024? Yeah. So it's like 0.001. What about, somebody help me out with the calculator, what about negative 30? 2 to the negative 30. That's right. I got you. So 2 to the negative 30. I don't know if you guys remember what this means. Times 10 to the negative 10. So that would be 0.90 9. So 0.00000000. I lost it. It's just stupid small, right? But I don't care how big negative I make this. Will the result here ever go 0? It can't. It's always going to be some very small positive number. It's going to be 1 over a billion, 1 over a billion to the billionth power, 1 over a trillion to the trillionth power. Holy shit. My point is, the really interesting thing that happens right here is it just gets closer and closer and never gets there. Anybody know what that's called? Sounds like it's a math insult. You're such a... Man, a lot of bad math jokes. I'm really sorry. I don't know if you guys are an asymptote. It's called an asymptote. I think I put that down here somewhere. Here we go. At the very bottom it says, notice that the y values get closer and closer to 0 but never reach it. The x-axis is called an asymptote. So when you make this graph, don't cross the x-axis. It can't. There's a stupid, there's a lot of stupidity. It's not stupid, let me try this again. When I first heard it, I thought it was kind of dumb. There's this thing called Zeno's paradox. Anybody ever heard of that? Sounds like a good band name, but Zeno's paradox is this guy named Zeno. There's so many things about it. If you tell Zeno to go to the next town over, will he ever make it there? No, he's never going to make it there. Because he's got to go halfway, right? And then he's got to go half of that distance. And then he's got to go half of that distance. And then he's got to go half of that distance. So he's never going to make it there. So when I first heard that, being the smartass I am, I said, well, just tell Zeno the freaking town is twice as far away as it really is. When he goes half, he's there. It's the end of your freaking paradox. And the teacher's like, shit. Anyway, has anybody ever heard of that? You guys get the idea? That, now obviously we get places. I got to go halfway. I got to go halfway. I get to the freaking table. I do, right? And that's got a lot more to do with physics and shit. But this is a beautiful example how pure numbers can do that. It's never going to get to the x-axis. It's going to get as close as you want it to, and then half that distance, and then half that distance. And there you can just keep doing that forever. Because the numbers go to infinity. So it's just never going to, it's going to get infinitesimally close to it. All right, enough of that. Enough. What's the domain of this function? What's the domain? What's domain relate to? What letter? X. What are the x's? What x's am I allowed to use? Look, I used negative 30 here. Can I use negative 300? Yeah, I can raise 2 to the negative. Can I use 1,000? 2 to the 1,000. Can I do it? Sure. Is there any number I can't raise to 2? No, I can use every number I want to. So what's the domain?
Infinity.
Now what about the range? What outputs come out of here? What's the lowest output that it almost gets to? I love you guys. It gets, what output? It has an output of 2, it has an output of 1, it has an output of 1/2, it has an output of 1 over 2 to the 10th. What's the smallest output that it almost gets to? 0. So from 0 to infinity. So the outputs, what y values does it go through? It doesn't quite get to 0, but it does go forever after that. Okay? Every single exponential function, any function that looks like this, will have this shape. I could actually do stuff and move it around, which is the next thing I'd want to do, but we don't have time to do. That's going to move it somewhere. That's going to move it somewhere. But it's going to still have the same shape. Just like parabolas, what can they do? Their vertex can change, go up and down and over. It can flip. Same stuff can happen to this. Same stuff can happen to any function. They can move, they can flip. All right, that's enough. I'll see some of you guys in a few minutes. Yes?
We're talking about the